Well, hello, welcome to the virtual panel for this afternoon on discussing our virtual ocean observations that we have in place. Are the slides up for this? Great, thanks. Welcome to our virtual panel this afternoon at Capitol Hill Ocean Week 2024. This is all about advancements for observing our ocean. And I'm really excited here to be here today with Shelley Tomlinson from NOS and Kim Hyde from Fisheries. And we'll be talking about some exciting upcoming systems for observing our oceans. These are the systems that we depend on to deliver the service and information that drives the NOAA mission, applies it to the commercial sector and every public citizen in the United States. So we're excited to be here today to talk to you about this topic. Shelley Tomlinson is a research oceanographer with the National Ocean Service and the National Centers for Coastal Ocean Science in NOS. And she works in the harmful algal bloom forecasting branch. And Shelley has been in a central role in the development of harmful algal bloom forecasts in nearly 12 different locations on our coast and ever expanding, and is at the really pivotal in the discussion of how NOS is using observations to deliver our services through next generation forecasts. So welcome, Shelley.
Thanks.
And Kim Hyde is a biological oceanographer with the National Marine Fisheries Service at NOAA. Kim works at the Narragansett Bay Laboratory, which is part of the Northeast Fisheries Science Center, which has laboratories across New England. Kim is an absolute focal point for using satellite information for oceanography, ecosystem science, and is really the bridge of bringing these observations into use for advice on fisheries and protected species. And also led and developed some of the most exciting work that we do to understand the state of our ecosystems and as climate changes and we try to achieve a climate-ready fishery. So welcome, Kim. So this afternoon, I'll talk a little bit about our observations and what we're looking for, and then Shelley and Kim will both have a chance to make some statements, and then we'll have some questions to go back and forth and have an open discussion. So here we go. Observations that NOAA makes from satellite in situ and from our ships and aircraft and observers all form a large enterprise of observing across a broad array of topics, from anything from harmful algal blooms right into looking at protecting whales. And all of these observations with their broad application to the NOAA mission go right through and are available to the public and to our commercial partners so they can make decisions that they need. All of these operations are required and extremely valuable. If you look at some of the statistics on this slide, that $1.3 billion a year in damages from harmful algal blooms, as well as the threat of illnesses to humans, and we apply great effort to ensure our observations are driving those forecasts. Phytoplankton support a $260 billion a year fisheries economy. Information helps us protect whales, and information broadly helps us understand the ecosystem's response to climate change. Across the board, these observations really work to support a climate-ready nation, drive a new blue economy, and all the information from these observations are driven into and have equal access for everyone. Next slide. I'm psyched to talk to you today because it is such a unique time in ocean observations today. We sit here at CHOW in 2024, not too long after NASA's launch of its amazing PACE satellite. And I've said to others, I think at the moment we launched that satellite, the moment that NASA pushed the button on that, we really opened a new generation of ocean observing. The instruments aboard NASA PACE are of the highest technology and provide us with hyperspectral look, which is basically being able to look at an enormous amount of detail in what's happening in the Earth's oceans. But PACE is part of a whole evolution of satellites that we see in our constellations, following on, of course, building on our legacy from JPSS, but following through to a NASA GLIMR system. And the GLIMR satellite, with nearly the same specifications of PACE, will place the same instrument now in an orbit that allows it to stare at the Gulf of Mexico and give us images every hour at high resolution, unlocking the ability of not only seeing detail, but now seeing how the ocean moves and look at dynamics and opening up even more tools for us to use to meet our mission objectives. And later, as we begin in the 2030s and right through an almost entire generation of scientists, we'll launch the GeoXO constellation, a constellation with 6 planned satellites that houses all of the meteorological satellite instrumentation that we need to complete our mission to protect lives and property, but also includes next generation ocean instruments that work like PACE, like GLIMR, but now will be placed in an east and west position, focusing on almost the entirety of the US EEZ. This constellation, working for more than 20 years, will fuel operational systems, will fuel information that we can use to drive our mission forward. Beyond this, the sky's the limit with new technologies after the GeoXO constellation. So we're so excited to be here at this point in development, and the timing is perfect as the challenges in front of the oceans are great. The images below show in situ systems. We always build our constellations and we think about our observations in an enterprise way, and we depend on the in situ systems as well to make sure that we have a full and capable look at delivering the best ocean intelligence that we possibly can to achieve our objectives at our agency, help other agencies do the same, and to make sure that our commercial partners and the private citizen have access to this information. A bit more on GeoXO. So GeoXO has an ocean color instrument. It'll be placed in 4 satellites over about 20 to 25 years. And it's the instrument, we call it OCX on GeoXO. And there's a number of different applications that we're so excited to talk about, protecting things from oil spills, looking at how we work with advice on fisheries as ecosystem changes, fueling what happens on fish farming, shellfish farming, access to information on those conditions and threats, recreational fishing, looking at oceanographic forecasting, understanding the conditions and the visibility in the water, harmful algal bloom forecasting for public health, recreational purposes, both for recreational fishing and use of the coast. All these applications and many, many others will come from the instrumentation that we're putting aboard GeoXO, the instrument called OCX. Next slide. So overall, I think we have 3 great things that we always focus about as we look at the evolution of this amazing constellation before us from now today to almost to 2050, is we're achieving an understanding of the ocean and how it's dynamic, looking at not only super detail, but looking at how those things move during the day. They're going to unlock new forms of data, new analyses for us to use. It's going to be discerning. We're going to be able to identify more detail about what's in the water, and we're going to look at things in higher and higher resolution, so we can work not only in the open ocean, but on our coastal seas and right up into the coast. Next slide. A couple of goals that we have as we look forward, and I'll touch on those, is as we use this observational system in our observatories, one thing we're focused on is boosting the performance of ocean biology in the coastal seas. What you're seeing here is an image of a model grid and some model results from some of the best forecasts that we have that combine climate simulations, oceanography, and ecology to predict how ocean ecosystems will look into the future based on climate change. And these systems are dependent on great ocean biology on the coast. Next slide. Whenever we launch new satellites, as a government, and we collaborate with NASA and our partners around the world, we always think carefully about making sure that we build this careful long-term time series, this big record of all the parameters that mean so much to us. With many, many instruments in the equation, we have to make sure we can detect change very precisely. And to do that, we have to curate very nicely a long-term record of these parameters for us. So we're focused on that as well in the upcoming months. Next slide. Our satellites don't work alone. As I said before, in situ is very important. One of the most important members of in situ for the satellite operators are the buoys, moorings, and systems that help calibrate those satellites in space. The signal that we're looking for in the ocean is a very refined signal, and we have to be a highly calibrated, high-performance instrument. So we look for those instruments to have a next-generation ocean calibration network. What will get us through the next generation of oceanography to help keep these satellites calibrated? And where will we put them? In the challenging places on the coast where you need to have the highest performance, the biggest threats from climate. And what other instruments can we collaborate and put on these platforms so we can improve our environmental intelligence? Well, now I'm going to pass it over to Kim Hyde from the Northeast Fisheries Science Center and let her make a few remarks.
Thanks, Mike. I want to talk a little bit about how we're using some of these data products, current data products, and potentially new data products at fisheries, and how we're getting them into management and making them operational. So just a quick background on what NOAA Fisheries is responsible for, which is the stewardship of the nation's ocean resources and their habitat. But the main approach we're taking at this is from an ecosystem-based management, where we're trying to understand the entire ecosystem and how it's changing and how one component can affect another. So we can go to the next slide. And how we're doing that, at least in the Northeast, is through our State of the Ecosystem reports. So we produce these annual reports with ecosystem information and a synthesis of fishery information, and we present this to our managers, and we try to understand where we are seeing significant changes that are of concern and how they affect management objectives. So I'm going to present mostly what we're doing here in the Northeast. However, similar efforts are going on at other science centers throughout the US. So it's not unique to here, but they're all slightly different. So we're going to talk a little bit about the State of the Ecosystem report and how the satellite data is used in it. And then I'm going to talk just a touch on some new products we're working on for this project. So go ahead to the next slide. As we all know, the ecosystems are very complex and they're all affected by everything. So we like to use this theme of multiple system drivers. So where changes in the physics or chemistry can affect the biology, which can affect the human dimensions, but then human fishing pressures can again affect the biology. And so there's a big interconnection here. And so we can't just look at one component and make a decision. We need to see how that component is affecting everything else. So next, please. And so I said we're in the Northeast Shelf region. If I would give it 3 words of description, it's very dynamic. We have a lot of changing, we have a lot of currents. They're counterbalancing each other, but because of that, it makes it also very productive. Productive from a primary production aspect of phytoplankton and chlorophyll, which we can see through our chlorophyll imagery, but also productive in the fisheries aspect. And so it's a highly fished area of extreme importance, with, depending on either the first or the second most profitable fishery in the United States, most of that coming from our scallop fishery. And lastly, it's changing. It's changing very rapidly. It's warming faster than a lot of the other regions across the globe. And so it's really, really important to understand how those changes are affecting everything else in the ecosystem. So the important part is, when we're looking at management objectives, is understanding how things are changing spatially. Are we having our species moving further north? Are they going into deeper waters? Is it as productive in that region? And so that's a really important thing that we're watching for spatial movement of species of interest, because that will affect how we manage them. Next, please. Also of importance are the temporal changes. So what I'm showing here is these are just plots of phytoplankton biomass over the course of the year. And if we're having shifts in these peaks of timing, that can affect the rest of the trophic food level or food web. And so monitoring for changes in timing of events, and how changes in phytoplankton may affect changes in zooplankton, which could affect changes of spawning of other species. So those are very important. And then lastly, on the next slide, is just changes in overall productivity. And so the phytoplankton here are the base of this food web. They're of extreme importance, but it's important to understand how many phytoplankton are out there, how productive they are, and actually who is there, because that does make a difference when we're looking at the food web. And a lot of this is driven by, if you click next, on changes in, I don't know why it's doing that, but anyway, changes in the physics of the region and the changes in the chemistry, so availability of nutrients. All of this feeds into the upper trophic levels. It affects the fish condition. It affects predators and prey alike. So And eventually it affects seafood production and fishery availability. So this is why we're doing all of this work. Another important thing that I wanted to point out, we were monitoring last year, which was a huge event. In the Gulf of Maine, there was a very anomalous large bloom of this phytoplankton species. It's a dinoflagellate that we weren't expecting to see. It was this bloom that lasted throughout the late spring and throughout the summer. You can see in the bottom plot here where the green lines are just sort of off the scale of what we've normally seen. And this is really important because while we're providing a lot of productivity into the ecosystem, there is a huge effect on fisheries because, one, it wasn't appear to be grazed. And so we don't have, there happened to be a shellfish experiment going on at the same time, and these shellfish were not eating the phytoplankton like they normally would because for whatever reason, they did not like this phytoplankton species. And so that was a really interesting thing. And because we were kind of hoping it would better to happen this year, because then we would have had the new hyperspectral paste sensor that is up that could help us identify this species compared to other phytoplankton species that we would more likely expect to see. And it can also help us with identifying some of the water masses. And so that's the last project I'm going to briefly touch on the next slide is using our ocean color data, using our temperature satellite data, and how we can identify water masses. So there's a current product out there incorporating these types of information. But when we move to hyperspectral, we can see a lot more colors of the water, and we can look at how different water masses may appear different in color. And by doing that, we can distinguish nearby water sources, because when we have changes in our water sources into our region, that affects fisheries habitat. And you can hit the next slide. So what we're seeing is whenever we have changes in habitat where we're having warm offshore water moving onshore, it affects where the squid species are in our region. We also were observing aggregations of large whales last year associated with movement of a warm core ring onto the region. So the goal of our current work is to incorporate this more fine, detailed hyperspectral data and to be able to look at the optics and color of the water and incorporate that into a better, more regionally tuned model for identifying water masses in our region, and then comparing that to the habitat for various species. So the last slide here, I just want to say a quick thank you. There's several applications of ocean color and hyperspectral data for NOAA fisheries. I only had a couple minutes here, but I'll be happy to chat more about those later. And now Shelley is going to take over to tell us a little bit about more of the harmful algal bloom testing and monitoring.
Thanks, Kim. Yeah, thank you for having me here. I thank Mike for inviting me to this panel. I'm going to give you just a brief background on what we do in the realm of harmful algal bloom forecasting at the National Ocean Service, and touch on how some of these new tools could improve our current forecasts. Next slide. So for those of you who don't know what a harmful algal bloom is, the late Ted Schmeda from the University of Rhode Island, I think, said it very poignantly. It's the criterion to use in defining whether a harmful species is in bloom, and the distinctive feature of such blooms lie not in the level of abundance, but whether its occurrence has harmful consequences. Harmful algal blooms are tricky. Sometimes they dominate the phytoplankton and are visible by space. There are some species that are very toxic at low concentrations. So it's really the level of phytoplankton and type of phytoplankton that causes toxicity. Next slide. So I've been working for the last 20 years in trying to detect different types of phytoplankton from space using our current polar orbiting sensors, and then incorporating that and using that to initiate forecast models and monitoring systems for harmful algae. We use multiple methods to provide an early warning of when a harmful algal bloom is going to reach a beach or a drinking water facility to support state and local managers. This these aren't one-off products that we don't refine with the current research. So we do expand them with new algorithms from Ocean Color, and new remote sensing products. And it's a really exciting time to be a remote sensing scientist, working in HABs with these new tools that, Mike mentioned PACE and other things coming up the pipeline. And then we provide information using this new science to our stakeholders. We are constantly hearing from our state agencies and our county representatives that they want higher spatial resolution, more frequent observations, better lead time to manage whether it's a fishery or a beach or a public health entity, to improve the accuracy and timeliness of our forecasts. And while the satellites are a piece of this, we're really looking at an overall ocean observing system. Think of the weather. Weather has, a network of in-situ atmospheric sensors in addition to the satellites, and we're moving in that direction in the world of oceanography. So, the satellites capture the synoptic view, but we really rely on in-situ observations to tell us what's in the water, especially when it comes to harmful algae. Next slide. So I'm going to highlight two of our operational forecasts, and I'm not going to go into detail on them, but at least highlight where the satellite information comes into play. So first, this is the 20th anniversary of our Gulf of Mexico HAB forecasting going operational. My office was involved in developing that with our Gulf Coast partners. Next slide. And the problem in the Gulf of Mexico, and in particular the coasts of Florida and Texas, is a phytoplankton species called Crania brevis. It blooms almost annually, and I say that because we didn't really see much of a bloom last year. And it has negative impacts that, one, it produces a toxin that gets kicked up into the atmosphere as the cells break in the water due to wave and wind action, and it gets blown onto beaches, causing people to have respiratory irritation. I've heard you can feel like you're having an asthma attack when these toxins are in the air, eye irritation, etc. It's also an issue for shellfish. Neurotoxic shellfish poisoning causes shellfish beds to close, the commercial shellfish fishery up on the panhandle, and basically makes the shellfish toxic to eat. And then a whole suite of environmental animal deaths, et cetera, fish, benthic organisms, et cetera. I will say these blooms are very patchy. So if you're trying to detect a harmful algal bloom with just a couple in-situ sensors, it's really difficult to get a sense of how widespread the bloom is. And that's where the satellite imagery really comes into play. So they also vary with time. From one day to the next, these things move around. The species can swim, so it can come up and down in the water column. So trying to detect that is very important. So overall, we really want more timely, more information to limit health impacts of these blooms. Next slide. So I'm not going to go into detail on this slide, but there is a QR code there if you're interested more on our forecast. But basically what we're doing right now is a forecast that goes out 36 hours and is updated every 3 hours at individual beaches. This takes into account in-situ measurements of cell counts of the species, which is, we have a slew of partners, both from citizen science groups as well as state and county agencies collecting samples. We then take a National Weather Service wind model to forecast when these toxins are going to get blown onto the beach. And then we provide these reports, as I said, throughout the day. And our end users are broad, and I'm not going to go into all of the end users here, but it's, the common beach goer to the state agencies, et cetera. We also have an intensification forecast, which predicts, is the bloom going to get worse or better over the next 10 days at a particular beach or location. And again, this is a hydrodynamic model combined with this cell count information and the Weather Service wind forecasts. And then finally, to get to the satellite piece, we provide a nowcast, which is basically an 8-day snapshot of where we think the bloom is based on satellite imagery. And when I say it's an 8-day average, that's because we need to remove the clouds. And these are these polar orbiter sensors that we're currently using can't see through clouds. So we get one shot a day. And if you know, the bloom is in an area of clouds, or if the bloom has moved, we can't detect that. So we do an 8-day composite to remove that and give an estimate of where we think the bloom is. We're currently using a satellite called the Ocean Land Color Imager from EUMETSAT, our partners in the European Space Agency. So anyway, I mentioned these blooms are patchy. So having, you know, an 8-day composite is really not great at getting to forecasting toxins at a beach every day. Next slide. And then moving to the Great Lakes, in Lake Erie, we also produce a harmful algal bloom forecast for that region. Next slide. And the problem here is what's called cyanobacteria. There are annual blooms of these in the lake as well, and in other freshwater systems across the country. I'm going to focus strictly on Lake Erie here. These cyanobacteria produce a suite of toxins that can form scums at the surface and affect recreation activities, beachgoers, etc. You see, I think, a boat going through here spraying up these, you know, this bloom and toxins. We've seen jet skis going through the water. It affects animal health, and also drinking water is really the key thing here. And what our forecasts do is identify when and where these impacts will occur. Next slide. And in this system, we are incorporating the satellite imagery directly into the forecasts. And we've got kind of two pieces to this. There's a seasonal forecast where we kind of predict how bad the bloom is going to be over the next season. And if you're interested in that, there is a big rollout of this forecast happening on June 27th. You can use the QR code on the right to register for that. And this takes into information of phosphorus nutrient loads from our colleagues at Heidelberg University. It incorporates river forecasting from the Weather Service and other ensemble models with our academic partners. And again, this is to kind of give state agencies information on what do they need for the summer to ramp up for these, responding to these blooms. We then have a short-term forecast, which goes out 3 days, forecasting where the bloom is, the intensity, and where it's going to go over the following time, you know, several days. And this, again, is using that European Space Agency Copernicus satellite data, along with a model and in situ measurements. And then finally, we have a vertical mixing model, which predicts, helps to give us more information about when the bloom is going to be at the surface and how much we're picking up with the satellite imagery. But again, clouds are an issue in this as well. So we really rely on daily cloud-free ocean color for this. Next slide. So I mentioned that these blooms are patchy. I should have mentioned also with satellites, we can only tell you that there's a whole lot of phytoplankton in the water. We can't tell you what species it is or what types. So there's a lot. None of this happens without the ocean observing network. There are a lot of advances, which I won't have time to go into detail. Everything from using an ESP to monitor for toxins and genetic information. We heard about eDNA this morning. That's all relevant to detecting HABs. Imaging flow cytobots, which is an imaging sensor which picks up, based on AI technology, what is in the water based on the size and shape of the phytoplankton themselves. Flow cams work a similar way. We have cheaper microscope camera systems to use this AI technology to deploy in citizen science groups. And we're using one called the HABscope for our forecasts in Florida. And then moving on to PACE, GLIMR, which we'll get to in a minute, and the hyperspectral sensors. There are all kinds of drones and UAS aircraft systems to capture the color of the water from space, or from above the water. And then the real goal is to get to toxins. Even if we see a phytoplankton that is probably a HAB, we can't tell you that it's toxic without measuring the toxins. That's how FDA regulates shellfish. A lot of this is dependent on toxins. So there's all kinds of technologies there that are important. So again, I mentioned the in-situ sensing is really critical to filling in the gaps from the satellites. Next slide. And then to pull this all together, there is now a framework within the community involving the National IUs Association and members of my center, National Center for Coastal Ocean Science, and the academic community to try to pull together all of this information to create a complete HAB observing network. And around the country. And so I'm going to stop there so that we have time for questions. Next slide.
Great.
Oh, sorry. And then we're going to talk about this, but the future is this sort of geostationary, hyperspectral suite combined with the in-situ to get at better separation of phytoplankton, being able to tell a group what kind of phytoplankton's in the water, how much is out there, where it is along the coast, and where potential toxin events might occur.
Thanks, Shelley. And thanks, Kim, for those remarks too. It was a great couple of examples along a few different lines of how we go from the observatories that we've deployed, both satellite and in situ, to the advice that we provide, the models, the simulations, the analysis, and the forecasts. And it was great to see that rich detail, and you can hear some of the challenges there. I want to talk a little bit about what we started with was this evolution of these ocean viewing satellites. And our friends at NASA launched a killer satellite with PACE that really set the standard for that type of instrument. And we'll see that move through GLIMR and with GeoXO to have sort of the full expression of the power of that. I'd like each of you, and I'll start with Kim, to talk a little bit about what some of those characteristics, some of the specifications that you see in those upcoming instruments that get you excited from your vantage point in the work that you do.
Well, I think with the new hyperspectral data, we're just going to be able to see a lot more things in the water, which is really good because right now we are limited by just a few colors, and it affects our ability just to even get at basic information, which right now ocean color was aimed at getting chlorophyll concentration. So understanding the total amount of phytoplankton that are in the water. But other things, when we're closer to the coast, get in the way. So whenever there's other, what I just like to call junk in the water that affect the color that the satellites are seeing, we cannot get an accurate estimate of the total amount of phytoplankton. So I think just with this hyperspectral data where we can tease that out and tease down so we get at the specific signal, that's great. And then the next step is distinguishing these different types of phytoplankton groups, because not all phytoplankton are equal, and there's some that are much more nutritious and are the primary source for the food web. And those are the ones we're really interested in understanding how much of the larger phytoplankton are there and how much are then getting into the food web. So we can understand based off of the primary production, what's the total amount of production we could expect in the ecosystem. And that relates to how much we can fish from the ecosystem sustainably.
Great. Yeah. It's all about kind of getting that understanding. Yeah, Shelley, same question to you.
Yeah, so Kim mentioned trying to figure out the amount of the phytoplankton. Well, I want to get to what type, people throw around species. I don't think we'll get that far, but at least to a group of phytoplankton to determine, is it more likely a toxic species versus a non-toxic species for the HAB piece of this. And I work in really cruddy coastal waters. So a lot of this separating out not only the sediment and what we call dissolved organic matter from the signal, but also looking at, is it more likely a dinoflagellate, which is a type that tends to be more toxic, while there are some diatoms and other things that produce toxins as well, to give, our stakeholders more information as to, do they need to ramp up sampling or get out there and monitor for toxins, close down shellfish beds, and provide early, warning signs and that sort of thing. So yeah, we are already actually bringing in PACE data to try and recreate the current sensors that we use, more to get one shot a day, but we're really at a research phase now with hyperspectral, and I'm excited to see what we can tease out of it on individual phytoplankton types.
That's great. Thanks. So the next question I have is sort of, we're sitting here now at CHOW in 2024, and what's next? What couple of things do you guys see kind of, I'll start with Kim again. What do you see kind of coming down the line in the next year? Like, what exciting new developments might we hear about next year at CHOW, from the work that you do?
Well, I'm really hoping we'll have a much better handle on our new water mass detection algorithm, and so that we can look for changes in water masses. I think that's going to be that's our primary focus for the next 12 months. But we will, in the meantime, we're also going to be collecting a lot of in-situ data. So NOAA Fisheries has several surveys that they go out. So we're going to piggyback on a few surveys this upcoming year and go out and collect data, which will give us that opportunity to validate the new PACE satellite data and just make sure we're seeing what we expect to be seeing, and we can then decrease our uncertainty in the products that we are producing. So by knowing we're doing a really good job, the satellite's doing a really good job of capturing what we're seeing in the ocean, that we're going to have even more certainty in the products we're producing. So that's, I think, another exciting thing that's going to be coming out of PACE, is just this increased certainty in what we've got.
That's fantastic. Yeah, that's great to hear. Shelley.
Yeah, so right now we have sort of a bunch of regional forecasts that are several operational, some in demonstration phase. And what I really am looking forward to seeing is sort of a national system of forecasts, where, for instance, there's an event going on the West Coast right now in Oregon and Washington, where people have been hospitalized for PSP, toxins from a species called Alexandrium. And we are all ramping up. It's unusual. So looking at satellite imagery to see if we can pick it up, but there's just not a real-time system right now for monitoring our coastal oceans for HABs. So I'm hoping we're moving in that direction. In addition, adding these new technologies to pick up, provide more information about what's in the water. And then looking forward, for new students and that sort of thing. I mean, this is big data, and we're going to have to figure out how to manage that. So I don't know, we may be getting that question anyway, but yeah, just a lot of it's an exciting time to be in this discipline.
Yeah, it is. Thanks for that. I mean, I think it is a great time. I mean, it is quite remarkable that if we take a look at now moving from what NASA has for PACE and potentially for GLIMR, and finally bringing that together with GeoXO and a satellite constellation that's really fulfilling our requirements. We're looking really carefully at what our mandates say, from Magnuson-Stevens Act through Marine Mammal Protection Act, Endangered Species Act, right through the HAB-HARCA and Restore Act, and others, and many other objectives that we have for observing are all built into those satellite constellations. And that system is allowing us to look at our own US EEZ in a way that we've never been able to do before. Hyperspectral, super high resolution, and super high updates just unlock a lot of what you have been talking about, both of you have been talking about today. I wonder if we talk a little bit about just a comment, and I can start with you, Shelley. There's this interplay, and both of you mentioned this kind of interplay with in-situ systems, ship sampling, and tell me a little bit about how that for you works together, as that really becomes this kind of enterprise of systems that has, of course, the satellite assets in place, but also a good network of ocean observing.
Yeah, so in our realm, we need real-time information to predict what's going on, on that sub-daily timescale. So having not only the instrumentation in the water or from space, we need a real quick refresh rate of that data. So getting the measurement at the water level to our forecast office to then provide into a forecast within hours, right? That's really the goal. It's very piecemeal depending on region, how that connection from sensor to us happens. So I think that's probably one of the biggest challenges. And now also, bringing in these other streams of satellite data to initiate our models and assimilate them into the forecasting.
That's great.
So I would say beyond just the validation of the satellite data itself, it's also capturing what's going on underneath the surface of the water. So the satellite, for an ocean color sensor, we're only seeing the top few meters of the ocean, but a lot of information is missed at subsurface. And so collecting that in situ data helps us understand what the vertical profile looks like. And this information can be used to understand if maybe we have a lot of phytoplankton subsurface, but we have at the surface, we have a minimum because there's just not enough nutrients to support the surface phytoplankton. But at the same time, then this in situ data can also get fed into biogeochemical models that can help us, again, better understand this three-dimensional ocean that we're trying to monitor and manage. So the more of this in situ data that we can assimilate into biogeochemical models, the better we understand what's going on at depth is great. And then the next step will then be leading into the ecological forecasting. So can we do short-term, mid-term, and longer-term ecological forecasting to predict how climate change is going to affect our ecosystem and the species we're managing?
I wanted to touch really quickly and start with you, Shelley, on the theme of CHOW in 2024 is leadership, and thinking about students, training opportunity, early career scientists and professionals. What do you see as emerging needs and opportunities opening up, and a message to those individuals that might be listening in?
Sure. So I see kind of three different areas where there's a huge need. One with this hyperspectral data, like the traditional way of developing algorithms is changing from ocean color. I think there's going to be a reliance on using some AI and cloud computing to work with that huge amount of data, especially adding the temporal and the higher spatial resolutions. So, those in the computer science, realm, working with big ocean data is important. Ecological modeling, it's really hard to find good numerical modelers right now who are used to working with this data, assimilating it into circulation models and adding the biological piece to that. So I think that's a huge area where we need more growth in our universities. And then I mentioned image classification, again, an AI kind of area for a lot of these in situ sensors and trying to look at, species recognition software and developing code where we can automatically get information on what's there.
Cool. To you, Kim.
I'm going to echo a lot of what Shelley mentioned, but maybe to add on to that, I think a couple of the areas that we are really pushing forward with is open science. So developing means of having reproducible and transparent and accessible science so that we can go back and reproduce our work, or somebody else can take a look at it and learn from us. And this open collaboration, I think, is very important. And then I had another great idea and it just lost me there. Oh, the communication. So the visualization of the data. So being able to take what really is a complicated thing and messaging it out into a broader audience that can be easily understood. So visualizing data, communicating that data, and that outreach, I think, is also another great skill that more of us need to work on. And so I think that's another great thing. And we have a lot of new early career scientists working with us now, and it's great to sort of see them pushing us forward in these types of avenues. And it's an exciting time right now.
I totally agree. With the Next Generation Observatory, we get the next generation workforce in place. That's so great. Well, that wraps up our panel. Thanks, Shelley, and thanks, Kim. This was super easy. I've had a pleasure working with you guys for years, and it was so nice to be able to chat with you here at CHOW in 2024. I want to thank our NOAA team that supported us and helped develop this panel. Certainly thanks to Capitol Hill Ocean Week 2024 for the opportunity to discuss this. And thank you to all that connected and listened to our presentations and our discussions today. And NOAA is working hard with its partners like at NASA and other agencies and the commercial and private citizens on really maintaining its position as being a trusted source, an authoritative source on environmental information to solve the challenges for our oceans. So thank you very much, and hope you enjoy the rest of your afternoon and the last day of CHOW here today. So thank you.
Thanks, Mike.